Good morning, afternoon, and evening to everybody. We have Yash Mishra. He's going to be here talking about Kubernetes and Azure and HPCC Systems. Yash is a graduate student at Clemson University, and he had the opportunity to intern with us over the summer. He's been working for quite some time, but before and after, to evaluate HPCC under Kubernetes on the cloud platform and how it compares to the legacy on-prem configurations. So without further ado, I'll let Yash take it from here. Thank you.
Thanks, Dan, for the warm introduction. I'm delighted to talk today about the Kubernetes aspects with HPCC Systems on the Cloud Native roadmap. This project actually builds on the work HPCC Systems development team has been doing with the Cloud Native aspects and along with containerization. Here's a quick outline of my talk today, starting off with the motivation and then jumping right into the world of containers and Kubernetes. Then we explore orchestration with Azure Kubernetes Services and configuration aspects of storage and networking in Kubernetes. Then we take a look into what the challenges were and then the cost considerations, followed by where the project is and where it's headed. So let's get started. Cloud-native systems take full advantage of the cloud service model. Designed to thrive in a dynamic, virtualized cloud environment, these systems make extensive use of platform as a service, compute infrastructure, and managed services. They treat the underlying infrastructure as disposable, provisioned in minutes, and resized, scaled, or moved or destroyed on demand via automation. Deployment of HPCC systems to commercial clouds can be done in multiple ways, depending on various business needs. While lift and shift is one way to go, which involves moving of unchanged application infrastructure from on-premises to the cloud-based on virtual machine approach, containerization of the application with the aim to go cloud native is another approach. The recent push of HPCC systems to go cloud native involves this containerization strategy, which provides a logical packaging mechanism in which HPCC systems resources are abstracted from the environment in which they run with multiple containers running on top of the operating system kernel directly. And, and the goal of this project is also to further the understanding of how HPCC systems runs in the cloud native environment with an effort to help meet business needs. And we have used Azure as a target in this project, and also with the effort to compare HPCC systems with the legacy version and the containerized version. Containers. Before digging into the Kubernetes support for HPCC systems, let's take a moment to understand what containers are. Just as shipping industries use physical containers to isolate different cargoes, for example, to transport ships and trains, software development technologies increasingly use an approach called containerization. Containers are essentially a standard unit of software that builds an application's code together with the related configuration files, libraries, along with the dependencies required for the app to run. This allows developers and IT professionals to deploy applications seamlessly across environments. Containers provide isolated operating system level virtualization. Multiple containers can run on the same machine and share the operating system kernel with other containers while being logically isolated, and this makes them lightweight and portable. Containers also don't require an operating system per application. A quick look into virtual machines versus containers. On a high level, virtual machines virtualize the underlying hardware so that multiple operating system instances can run on the hardware. Each virtual machine runs an operating system and has access to virtualized resources representing the underlying hardware. A container, on the other hand, virtualizes the operating system and causes the containerized app to perceive that it has an operating system, including CPU, memory, file storage, and network connections all to itself. Now, as I mentioned earlier, multiple containers can share a single OS, making them lightweight. Each virtual As application development moves towards a container-based approach, the need to orchestrate and manage those resources is also important. And that's where Kubernetes comes in. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. The focus is on the application workloads and not the underlying infrastructure components. Kubernetes provides a declarative approach to deployments backed by a robust set of APIs for management operations. It was designed by Google and now maintained by the Cloud Native Computing Foundation. An interesting thing to note is that Kubernetes is not monolithic, and these default solutions are optional and pluggable. A quick look into the terminologies associated with Kubernetes. Containers, as I mentioned earlier, are a lightweight and portable executable image that contains software and all of its dependencies. Pods. Now, pod is a Kubernetes specific terminology. A pod, as in a pod of whales or peapod, is a group of one or more containers with shared storage network resources and a specification for how to run those containers. A replica set aims to maintain a set of replica pods running at any given time. Kube control is a command line tool for communicating with the Kubernetes API server. Kubelet is an agent that runs on each node in the cluster and makes sure that containers are running in the pod. For security, a secret stores sensitive information such as passwords, authorization tokens, and SSH keys. Role-based access control, or RBAC, provides access to control resources for users based on the least privilege principle, which means that users are only given permissions for the job, just enough for the job to be run. A job creates one or more pods and ensures that specified number of them are successfully terminated. A deployment provides declarative updates for pods and replica sets. Usually, you don't need to create pods directly, even singleton pods. Instead, you can create them using workloads such as deployments or job. Now, storage and networking, we will also go further into this presentation. And a quick understanding of storage is that in Kubernetes, storage has three aspects: storage class, persistent volumes, and persistent volume claims. And under networking, we have kubeproxy and ingress. And now the question is, why Kubernetes? Keeping containerized apps up and running can be complex because they often involve many containers deployed across different machines. Kubernetes provides a way to schedule and deploy those containers. Plus, it scales them to your desired state and manage their life cycle. Using Kubernetes to implement your container-based applications makes it portable, scalable, and extensive. And it also has a self-healing nature. That is, with pods and replica sets that we had just taken a look at in the previous slide. If if there is a pod failure due to any unforeseen circumstances, replica sets are quickly provisioned up in an effort to minimize the downtime for the application. Now, containerized HPCC systems. In the new Kubernetes version, several things in HPCC systems appear to be different than in the legacy version. HPCC components are converted to pods, completely decoupling it from node-level architecture. For example, engines like ECL Query, ECL Services, ECL Watch, HTOR, Thor Agent, MyDali, Roxy are running as logically independent processes in their corresponding pods. Now, pods run the system processes that communicate with other pods in the cluster, and them to roll over into a new pod in case a running pod fails to make it more available. Azure. Now, Azure is a commercial cloud platform which is managed by Microsoft. And just like any other cloud providers like AWS and Azure, it provides on-demand provisioning of resources, and users pay only for what they use. It offers cloud service models like software as a service, platform as a service, infrastructure as a service. And a quick fact, as per Azure's recent report, more than 90% of Fortune 500 companies run on the Microsoft Cloud. A look into how storage is handled in Azure and how it relates to HPCC systems. Azure Storage is a Microsoft managed cloud service that provides storage which is highly available, secure, durable, scalable, and redundant. Each service is accessed through a storage account. An Azure Storage account contains all of your storage data objects like blobs, files, tables, and disks. The storage account also provides a unique namespace for your storage data, which is accessible from anywhere in the world over HTTP or HTTPS. Data is highly durable, and the storage platform includes the following storage services: Azure Blobs, which are a massively scalable object store for text and binary data; Azure Files, which are managed file shares for cloud or on-premises deployment; and Azure Tables are a NoSQL store for schemaless storage of structured data. Azure Disks are block-level storage volumes for Azure virtual machines. There are two different storage account types, and with standard storage account, users get access to blob, table, and file storage, and the alternative premium account is the most recent storage option, which provides users with data storage on solid-state drives for better I/O performance. Now, the Kubernetes services under Azure. AKS, or Azure Kubernetes Services, is a managed Kubernetes offering which further simplifies the container-based application deployment and management. It handles the orchestration of container images. And for the pricing, since AKS is a managed service, users pay for the agent nodes, the storage, and networking resources. And there is no charge for managing the master node and the cluster itself. And just like any other cloud service provider, it has a shared responsibility model in which the service or AKS manages one part of the cluster, and users or customers manage other aspects of the clusters. Now let's take a look into who manages what and what the cluster architecture is. A Kubernetes cluster in Azure is divided into two components: control plane and nodes. Now, control plane nodes provide the core Kubernetes services and orchestration of application workloads. Nodes, on the other hand, run those application workloads. An AKS under the control plane, it provides a dedicated API server, scheduler, control manager, and etcd. Now, the kube API server, or the API server in this figure, is how the underlying Kubernetes APIs are exposed. This component provides the interaction for management tools such as kube control or the Kubernetes dashboard. etcd is used to manage the state of the cluster and configuration, and it is a highly available key value store within Kubernetes. Scheduler, or the kube scheduler, is when you create or scale the applications. It determines what nodes can run the workload and starts them. And the control manager oversees a number of smaller controllers that perform actions such as replicating pods and handling node operations. Going a little deeper into the customer managed side, the scenario looks like this. An AKS cluster has one or more nodes, which is essentially an Azure virtual machine that runs the Kubernetes node components and container runtime. The kubelet is the Kubernetes agent that processes the orchestration requests from the control plane and scheduling of running the requested containers. Virtual networking is handled by kube proxy on each node. The proxy routes network traffic and manages IP addressing for services and pods. The container runtime is the component that allows containerized applications to run and interact with additional resources such as the virtual network and storage. And the Azure virtual machine size for your nodes defines how many CPUs, how much memory, and the size and type of storage is available. Let's take a look into how storage is handled in Azure Kubernetes Services. And it is a bit different than in the traditional deployments. Applications that run in AKS may need to store data, which may or may not be shared between applications. And for some application workloads, this data storage can use local fast storage on the node that is no longer needed when the pods are deleted. while other application workloads may require storage that persists on regular data volumes within the Azure platform. Multiple pods may need to share the same data volumes or reattach data volumes if the pod is rescheduled on a different node. Finally, you may need to inject sensitive data or application configuration information into pods. Now, a volume represents a way to store, retrieve, and persist data across pods through the application lifecycle. A persistent volume is a storage resource created and managed by the Kubernetes API that can exist beyond the lifetime of an individual pod. Volumes that are defined and created as a part of the pod lifecycle only exist until the pod is deleted. Pods often expect the storage to remain if a pod is rescheduled on a different host during a maintenance event. A storage class defines the tiers of storage, such as premium or standard storage types. A persistent volume claim requests either disk or file storage of a particular storage class, access node, access mode, and size. And a persistent volume is bounded to a persistent volume claim once an available storage resource has been assigned to the pod requesting it. And there is usually a one-on-one mapping between persistent volume claims and the corresponding persistent volume. Traditional volumes to store and retrieve data are created as Kubernetes resources backed by Azure Storage. You can manually create these data volumes to be assigned to pods directly or have Kubernetes automatically create them for you. Now, these data volumes can use Azure disks or Azure files. Azure files can be used to provide shared file system backed by an Azure Storage account to pods. And files let you share data across multiple nodes and pods. They can use Azure Standard Storage backed by regular hard disk drives or Azure Premium Storage backed by high-performance solid-state drives. And this meets the shared data storage requirement for DLL storage and data storage classes in HPCC systems. Azure disks can be used to create a Kubernetes data disk resource. And just like Azure files, disks can also use premium storage backed by high performance SSDs or standard storage backed by regular hard disk drives. And it is interesting to note that Azure disks can be mounted as read write once, so it is only available to a single pod. And this does not meet the shared storage requirements for some of the HPCC engines, like data storage and DLL storage classes in a multi-node cluster. While on the other hand, Azure File Storage meets the shared data requirement between most of the HPC storage engines. Now, while Azure Disk Storage can still be used for certain HPCC systems engines like DALI storage, it does not meet the shared storage requirement for data storage and DLL storage classes. This is a quick define for the DALI storage in HPCC systems. It is a Helm snippet, and what is Helm? We'll take a look about that in a couple of slides. Now, this snippet creates a storage class for the DALI, as I had mentioned earlier, and the reclaim policy in this at the second from the last line controls the behavior of the underlying Azure storage when the pod is deleted and the persistent volume may no longer be required. And this snippet is for a persistent volume, which is or a persistent which is mounted as read write once, and since it is Azure Disk and mapped to the DALI storage under HPCC systems. Now, Azure disks or files are used to provide the persistent volume. As noted in the previous section on volumes, the choice of disks or files is often determined by the need for concurrent access to the data or the performance tier. Volumes that are defined and created as a part of the pod lifecycle only exist until the pod is deleted. Pods often expect the storage to remain if a pod is rescheduled on a different node. And if a pod is scheduled and requests storage that is not currently available, Kubernetes can create the underlying Azure disks. or file storage and attach it to the pod. And under this Helm snippet, it specifies the access mode and then the storage class name followed by the resources. And finally, the third aspect, or the persistent volume claim, which requests either disk or file storage of a particular storage class. Now, under AKS, there are 3 steps to create a to handle storage: creation of a storage class, followed by creation of a persistent volume, and then assigning a persistent volume claim for the corresponding storage class. The Kubernetes API server can dynamically provision the underlying storage resource in Azure if there is no existing resource to fulfill the claim based on the defined storage class. The pod definition includes the volume mount once the volume has been connected to the pod. And the following snippet creates a persistent volume claim reference for DALI storage class under HPCC systems. How AKS handles networking. To allow access to your application, or for application components to communicate with each other, Kubernetes provides an abstraction layer to virtual networking. In that, Kubernetes nodes are connected to a virtual network and can provide inbound and outbound connectivity for pods. The kube proxy component, which we took a look in the terminologies, runs on each node to provide these network features. In AKS, you can deploy a cluster that uses one of the following 2 network models: a kubenet networking and Azure Container Networking Interface, or CNI networking. In kubenet networking, the network resources are typically created and configured as the AKS cluster is deployed. And under CNI, the AKS cluster is connected to existing virtual network resources and configurations. The kubenet networking is the default option for configuration of AKS cluster creation. With kubenet, nodes get an IP address from the Azure Virtual Network subnet. Pods receive an IP address from a logically different address space to the Azure Virtual Network subnet of the nodes. Network address translation, or NAT, is then configured so that the pods can reach resources on the Azure Virtual Network. With Azure CNI, every pod gets an IP address from the subnet and can be accessed directly. These IP addresses must be unique across your network space and must be planned in advance. Each node has a configuration parameter for the maximum number of pods that it supports. The equivalent number of IP addresses per node are then reserved upfront for that node. This approach typically requires more planning, as can otherwise lead to an IP address exhaustion or the need to rebuild clusters in a larger subnet as your application demands grow. Moving on to the underlying network topology for HPCC systems deployed through AKS. Now, I apologize for the miniature fonts to show the entire topology. In an effort to map the new architecture, the new HPCC systems architecture under the Kubernetes deployment model with the following network topology, the main takeaway is as follows. At the very top is the virtual network that hosts the entire cluster. And then we have the virtual subnet where the Kubernetes cluster is hosted. Then boxed in green are the 2 node pools for the Kubernetes cluster. Boxed in, and then we have the network security group, which acts as a virtual firewall controlling traffic into the network. And then circled in blue are the route tables associated with the cluster. And then we have the virtual machines, which are hosted as a part of the node pool, under which the underlying pods run. And then boxed in red are the storage or the persistent volumes mounted for the corresponding nodes and pods. And then there's the load balancer, which controls traffic between the nodes or between the pods and the corresponding storage. And the load balancer also has associated health probes, which constantly keep checking the status of the pods, whether they are active or failed, in order to provision replica sets based on the responses. And then, of course, the outbound rules, which control the ingress access of network resources between the load balancer and the cluster resources. Now, Helm. From the steps that I had shown to create the storage class and the persistent volumes, which were essentially Helm manifests. And Helm is an open source packaging tool that helps you install and manage the lifecycle of Kubernetes applications. Similar to Linux packaging managers such as apt and yum, Helm is used to manage Kubernetes charts, which are packages of pre-configured Kubernetes resources. It works with a combination of templates and values. And the way it works is templates are created which include definitions of Kubernetes resources, and then values are assigned to define labels for the corresponding Kubernetes resources. And, and these values can be assigned externally on the fly at the time of installing Helm charts, or they can be assigned internally through the separate values file. And under HPCC systems, the Helm chart structure looks something as you see on the right side. There is the chart.yaml file, and then the values file, which specifies the values individual Kubernetes resources might have, such as the size of storage or the corresponding image of the Docker file, and then values JSON file, which is the same file as values, and the templates file, where all the HPCC components, which are containerized into respective containers like ECL server, Thor, HTHOR, have a corresponding Helm file associated with them for the cluster to be orchestrated via Azure Kubernetes Services. Now, the pod lifecycle under Kubernetes is as follows. Initially, right after deployment, the pods move into a pending state. And in this state, the pod has been accepted by the Kubernetes cluster, but one or more containers has not been set up and made ready to run. This also includes time a pod spends waiting to be scheduled, as well as the time spent downloading the container images over the network. Finally, I'm sorry. Next, they move into the running state, in which the pod has been bound to a node and all of the containers have been created. And at least one of the containers is still running or is in the process of starting or restarting. Then, under succeeded, all containers in the pod have terminated in success and will not be restarted. However, sometimes while all containers are terminated, uh, at some point, at least one container might terminate in failure. And in this case, the pod status moves to failed. For some reason, if the state of the pod could not be obtained, this makes the pod in an unknown state. And this phase typically occurs due to an error in communicating with the node where the pod should be running. And the specification of a pod has a restart policy field with possible values like always, on failure, and never. The default value is always. This restart policy applies to all containers in the pod. It only refers to restarts of the containers by the kubelet on the same node. After containers in a pod exit, the kubelet restarts them with an exponential backoff delay of 10 seconds, 20 seconds, 40 seconds, and so forth, that is capped at 5 minutes intervals. Once a container has executed with no problems for 10 minutes, the kubelet resets the restart backoff timer for that container. Moving on to quality of service for pods. After deployment, Kubernetes assigns one of the three quality of services to the pods, which are guaranteed, burstable, or best effort. Now, under guarantee, every container in the pod has a memory limit and request, and also a CPU memory and request to make sure that the resources are um, available on demand and that there is no downtime. Now, under burstable, the pod does not meet the criteria for a quality of service under guaranteed, And in this case, at least one container in the pod has a memory or CPU request. And in best effort, the containers need not have CPU or memory requests associated. For HPCC systems, the quality of service is guaranteed. Memory limits and memory requests are specified for containers. Similarly, CPU limits and requests are defined during the creation of Helm manifests. And the idea is to minimize downtime and guarantee service even during heavy traffic. Now, with a lot of aspects going on with orchestration and container images deployment, there some of the things that happen behind the scenes is that when a deployment is in progress, the Kubernetes scheduler starts assigning pods to nodes. And AKS being a managed service, some part of this is handled by that happens in the background. Containers are then created on the pods, and when a container is started, Node and Kubelet pull the container image from Docker Hub files. And in this case, the container images are pulled from the HPCC Systems Docker Hub files or your custom HPCC Systems Docker Hub files, which are you can directly include it from your GitHub repo. Scaling under Kubernetes. Now, the horizontal pod autoscaler, or HPA, used in Kubernetes monitors the resource demand and automatically scales the number of replicas. When you configure the horizontal pod autoscaler for a given deployment, you define the minimum and maximum number of replicas that can run. You also define the metric to monitor and base any scaling decisions such as CPU usage, for example. And based on CPU utilization or resource limits set forth in the Helm manifests for a container, HPA performs scaling of pods. In this example, the horizontal pod autoscaler for a Thor cluster scales the number of Thor worker pods from 2 to 4 based on the CPU resources, based on the CPU usage, in that if CPU usage goes beyond 70%, it scales out pods from 2 to 4 based on the pod limit of having up to 4 pods. And storage orchestration, as I talked about earlier, in that having persistent volumes followed by persistent volume claims for the corresponding storage classes, and then bounding the persistent volume claim to the pod. And with Azure Kubernetes Services, there are two storage classes, Azure Files and Azure Disks, that are compatible with the persistent volume aspects. However, Azure Files would also provide concurrent access to the files. Now, uh, with the development of the cloud-native HPCC systems platform being ongoing, the landing zone scenarios in Kubernetes was under deployment, and I hadn't had a chance to test with it with real data yet. A new release, 7.12.0, has just come out, and it does support it does have support for storage planes, and that which is also integrated with landing zones. It also leverages Azure Blob Storage, which is currently specified as a data plane under the Kubernetes architecture. For configuring storage in HPCC systems Kubernetes environment, another challenge is to be able to persist data. One option is to create Azure File Storage class through corresponding Azure Helm manifest. In this scenario, while HPCC storage classes, data storage, DLL storage, and DALI storage can reference the persistent volume claim for Azure File and execute ECL work units on the fly, it does not persist data at the moment longer than the Helm chart. And the idea is to make data persist longer than the Helm chart, by exploring alternative storage options like Azure Blob and comparing it with Azure File Storage. And this is still a work in progress. And in a future version, the storage classes may also be extended to target like Azure Blob Storage or Data Lake to see how storage itself gets handled under the Kubernetes architecture. And at a node level, the log contents of the log processing also becomes important to understand. And The logs in Kubernetes are typically ephemeral in nature and may be lost if the pod is evicted, the container crashes, or the node dies, etc. Also, due to the nature of the containerized solutions, related logs are likely to originate from various locations and might need to be collected and processed. One quick way to handle this would be to generate the logs and store them in an external file, which saves you the need to keep the cluster running even when your work unit has been finished, which saves you the cloud costs associated for having the cluster running when you don't need to. And now the cloud cost considerations, which is another aspect when working with clouds in general. Now, typically users only pay for compute, storage, and networking costs, and there is no charge for Kubernetes master or cluster management with Azure Kubernetes Services. Now, costs in this figure are split by service name on the left, location in the middle, and resource type on the right. Virtual machines typically comprise a huge chunk of the cloud costs incurred. For example, a standard DS2 V2 instance type costs about 14.6 cents per hour in the US East region, while it costs about 14 cents an hour in the US West region. Choosing a region may be cheaper, but it might also, or I mean, choosing a different region may be cheaper, but it might also impact the latency. And deploying in US East region versus let's say deploying in Japan, while one region may be cost effective, latency considerations might come into play. And since Thor is limited by the number of jobs, running a 10-way Thor in the US East region is likely going to be faster than running the same configuration in Japan. And another factor to note is that with big size data, the storage costs will also likely add up in the chart. For instance, testing with more real data, the percentage of storage costs associated would also take a significant chunk of the cloud costs which are built. And while the deployment of on cloud native roadmap is still ongoing, with identifying configuration options to run HPCC systems, in the current project, the cloud resource requirements are mapped with Azure resources at the compute, storage, and networking layers. Storage resources to handle the storage classes in HPCC systems like DALI storage, data storage, and DLL storage are provisioned. And the excuse me. Under the compute layer, this includes the virtual machine type for running the HPCC systems engine. For this, I considered standard B2MS and standard DS2 VM sizes based on their CPU to memory ratio, which is around 1:4, and compute costs, since they are less expensive than the higher end nodes. Under the storage layer, the storage capabilities are equally important. The amount of CPU and memory isn't the only factor when you choose a VM size. This also includes the virtual machine type for running the HPCC systems at the compute layer. For example, both the standard B2MS and standard DS2 VM sizes include a similar amount of CPU and memory resources. The potential storage performance is different. Standard DS2 allows double the number of attached disks and provides 3 to 4 times the IOPS and disk throughput. If you only looked at the core compute resources and compare costs, you may choose the standard B2MS have uh, as a less expensive option, but you may have a poor storage performance and limitations associated with the standard B2MS. And at the networking layer, the traffic control rules, the ports for HPCC pods, and the corresponding processes to run, the ingress traffic and protocols are mapped with the corresponding resources and Azure using virtual networks and kubelet networking, which helps us to generate a proof of concept HPCC systems deployment on Azure, and as well as under the Azure Kubernetes service. And much more to come. With the release of the new 7.12.0 and the support for storage planes, the next stages would be to perform a comparison to run a performance test with using a real-time data and comparing it with the legacy versions of HPCC systems. This would also help study the comparisons between a containerized environment versus a virtual machine environment on the Azure side. And the storage planes also would help us study the support of Azure Blob Storage under the new Kubernetes architecture. And with all the work ongoing, it will be interesting to see the roadmap under the cloud native scenario. And with this, I conclude my presentation. And thanks, Dan, for helping moderate this talk. And thank you, Lorraine, for extending this opportunity for me to speak. It has been a unique experience under the new virtual style. And now I'll be happy to answer questions from the audience. And if I run out of time, feel free to email me the questions and I'll try to answer them as fast as I can. Thanks.
Awesome. Thank you, Yash. I have a few questions. Earlier, you had mentioned something about virtual machine scale sets and virtual machines. What is the difference in Azure?
Correct. Well, that's a good question, Dan, certainly. So virtual machine scale sets are the auto scaling groups under Azure. And they are essentially virtual machines, but with the option to automatically scale out and scale in based on the metrics, which are CPU usage or the number of nodes. While virtual machines, on the other hand, are individual virtual machines that can also be scaled, but with manual configuration for scaling.
Okay, that makes sense. That makes sense. Also, I had a question about blob storage. So when would you use blob storage with HPCC versus some of the other blob storage options that you had outlined?
Like versus with blob storage for HPCC versus the Azure file storage, like the current under the current environment with Azure file storage, the file shares provide a concurrent access and the shared resources and the shared storage between HPCC engines. While for Azure blob storage, it would uh, 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 I'll plan to explore the reading of data from Azure blob, like the type, whether it is an unstructured data or uh, or a page blob that needs to be read, and assess how reading from blob is different versus reading from an Azure file.
Okay, that makes sense. That makes sense. Very good. Are there any other questions out there? If you have any questions, please post them in the chat and we'll relay them to Yash and we can get them answered. In the meantime, I have one more question. I know some of your slides had very specific timing and cost analysis and things like that. How did you test your Kubernetes installations if you couldn't use persistent data? I mean, at least large amounts of persistent data, because as you mentioned, 7.12, which was just released, has support for landing zone support for getting data in and out of that cluster. So how did you test prior to 7.12?
Oh, that's an excellent question. And identifying something to test the Kubernetes configuration was a good journey. And for running preliminary tests, I used the ECL performance bundle, which does not rely on external data and uses data generated on the fly to test the memory and CPU usages for HPCC systems. It is like a performance test bundle, and it's leverage that for the Kubernetes version.
Awesome. All right, very good. I don't see anybody lighting up the chat, so I think you must have covered everything very well. I believe we can end just a minute or two early and let people move on to the next item. And I wanted to remind the audience, we have an interactive expo booth and poster display is up next. So please visit. Please vote for your favorite poster. Yash has a poster there, and I'm sure you head over there and give a green thumbs up for Yash's work. It's very good. Anyway, thank you all for viewing and attending, and we appreciate it. Have a good rest of the presentations. Thank you.